Hello, everyone, and thank you for joining the session, whether you're here in person in Boston or joining virtually. I will be presenting our work today. This was a collaboration between Dynatrace Research in Austria, Graz University of Technology, and the CISPA Helmholtz Center for Information Security. So kind of the motivation for this work is some of the horrifying code we see here. So microarchitectural attacks, as I'm sure many of you are aware and know from experience, can be quite complicated to implement. They can be quite frustrating. Even if you're familiar with systems programming and working in assembly, we're trying to do things here that aren't supposed to be done. We're trying to access values that aren't meant to be architecturally accessible. So we do some really weird stuff, and it can be very difficult to explain your code to other people. It can be difficult to explain the code to yourself when you come back to it after a year or so. So these attacks are super complex to implement. This is slowing progress in attack research, and it's a barrier to entry for the field. It makes teaching microarchitectural security really challenging, and it also increases the risk that our mitigations are incomplete if even implementing an attack to test our mitigations against is quite challenging, and we don't know if we've got it right. So we asked ourselves, what does the attack development process look like in these three contexts of attack research, teaching, and mitigation? And how similar are these three contexts? Are they maybe similar enough that we can meaningfully talk about some kind of common attack development process? And if they are, could we maybe facilitate the development process for all three of them? Spoiler alert, they are similar enough. So we did the first systematization of the microarchitectural attack development process. We did a mixed methods analysis, combining a literature review of prior work, expert interviews with 16 practitioners from academia and industry, and a user study with 28 graduate students who were taking an introductory course in side channels and microarchitectural attacks. And we focused on 4 research topics. Firstly, the attack building blocks, so the core snippets of code that are being used to implement these attacks. And obviously every attack is slightly different, but we found there were some common building blocks that were occurring again and again. For example, high resolution timers, cache attack primitives, the ability to modify page tables. Secondly, we also looked into microarchitectural control and techniques that people have developed for fine-grained control so that we can have reliable attacks, reliable experimental results. Thirdly, the programming languages that people are using and the existing tooling. There were some existing microarchitectural attack development libraries, and we evaluated those in our user study. And finally, the overall development process, so things like key communication challenges and whether the development process was iterative. So for the full insights, I'd invite you to take a look at our paper, but I would say some of the most interesting insights were firstly that we found practitioners were doing a mix of evolutionary prototyping, so starting from an initial attack POC and iteratively improving upon it, and also throwaway prototyping. So these are one-off experiments where we might be trying to test a hypothesis about where the leakage comes from, which microarchitectural element it is, or perhaps just an attack idea that didn't work out. And even these throwaway ones, even the ones that get thrown away, never make it into the paper, are a crucial part of the attack development process. The final attack wouldn't be there if we hadn't had this initial work. Practitioners also always begin in C or assembly for maximum control. So even if we're trying to make a browser-based attack, we start off in native code. Because if you start implementing in JavaScript straight away, there's just too many variables to control, too many things that could go wrong if you're trying to debug why you haven't got leakage. It's very difficult to isolate what's wrong. Also, a lot of time goes into developing custom drivers or custom operating systems. These are often required for the privileged building blocks for attacks. For example, the ability to modify page tables or to read and write model-specific registers. As you can imagine, there's a lot of maintenance effort involved in that. It's a big initial time investment, but also needs maintaining as, for example, the Linux kernel gets updated. And proofs of concept can be really powerful communication tools. And the obvious example here is in the disclosure process when we present a POC to a manufacturer. But complexity makes them less effective. And even within a research group, we heard from practitioners that sometimes they had difficulty understanding proofs of concept from their collaborators. For example, might be a POC that they can't run on their own system because they don't have Intel SGX. We're looking at some strange assembly and trying to make sense of what's going on there. So based on this analysis, we determined that the best way we could facilitate the attack development process was by improving upon the existing software tooling to try and reduce the complexity of this implementation. We developed two frameworks. The first one was libtea, which is a cross-platform attack development API in C. Provides 142 functions for the most common attack building blocks that we identified. It supports Linux, Windows, and Android, which means you can run it on your phone, and we did. And it's a single C header with a supporting kernel driver, so it's quite easy to integrate into existing projects. And for our privileged building blocks, we built upon existing work with PT Editor for modifying page tables and SGX step for fine-grained control over Intel SGX. Secondly, we built SCFirefox. This is a modified version of the Firefox browser, which provides the functionality of libtea in JavaScript. Why would we want to do this? Well, this means that we don't need to port an attack PoC we have in native code completely over to JavaScript in one go. We can basically take our native code proof of concept, use exactly the same functions, so it's almost a native code proof of concept in the browser, and then building block by building block, replace it with vanilla JavaScript or WebAssembly. And doing this step-by-step process makes the attack development process much easier. So this framework can be used directly in the JavaScript shell, as SpiderMonkey, Firefox's JavaScript engine, or in the browser if you want to investigate interactions with the user interface as well. One limitation is we have some overhead from the JS API wrapper, so when we switch execution context from JavaScript to C++, that incurs a bit of overhead. It means that you can't run libtea functions speculatively. So some of your core attack primitives do still need to be implemented in JavaScript. So with these two frameworks, we determined a process that we call rapid prototyping, which is inspired by the use of rapid prototyping in other industries. And I stress here, we didn't just pluck this out of thin air. This really is based on the process that we heard from practitioners. What was really interesting, though, was that everyone we interviewed stressed they didn't have any kind of common attack development process. And every attack's different. Development always varies. I don't really know what I'm doing. I'm like stumbling around in the dark with these experiments. But hearing from so many practitioners across so many different attacks, we really could see that the process was very iterative, even if that wasn't clear to practitioners themselves. And I can say from experience implementing attacks, often it does feel just super frustrating and unclear. When you take the high-level perspective, we're starting from a hypothesis, we implement that in native code, and then using SCFirefox, as I mentioned, we can take that straight to the browser. And now we can start thinking about replacing each one of those building blocks, step by step. We might need to go back to libtea and iterate backwards and forwards because we might have some building blocks that have never been implemented in JavaScript before. So we need to do some experiments to understand how we can achieve that. And eventually we get our fully fledged attack proof of concept. Let's make this a bit more concrete with an example, ZombieLoad in JavaScript. So to recap, ZombieLoad is a microarchitectural data sampling attack where we sample data from the line fill buffers in the CPU. It's triggered by a zombie load. So that's a load that faults, triggering a microcode assist. And transiently, some data is returned from this faulting load, but it's not the data we tried to access. It's data from the line fill buffers, whatever happened to be there at the time. So as you can see here, we've got the line fill buffer. And this is a really interesting target because any loads on the sibling hyperthread are going to come through the line fill buffer into the L1 cache, so we can pick up on these. We decided to implement ZombieLoad variant 3 because it's the most practical one for an unprivileged attacker. And here we need 4 building blocks. We need 2 mappings to the same physical address. We need to have the access bit cleared on one mapping to trigger a microcode assist. Also, we need a way to flush the other mapping at the same time. This causes a cache line conflict and is also a crucial part of creating this zombie load. And we need a way to transiently encode and recover the leaked data, which will be a cache covert channel, as has been demonstrated in a lot of prior work. So here is libtea in action. This is the API. I apologize, we got quite so much crammed on one slide, but what I really wanted to illustrate here is that we don't need many lines of code. And we tried with the API to make things as conceptual as possible. So get away from that sort of overhead of thinking about the implementation details. Let's clear the access bit, for example, in one line. And in our core attack loop, you can see it's as simple as just saying flush our first mapping. Then we have this speculation start and end block, which looks a bit like an if block. That is actually hiding some assembly code. But we don't need to care about that. We don't want to. We want to work at a higher abstraction level. So within this block, we have our 2 instructions that are going to be run speculatively. The libtea access to 0 is extending our transient window. And then we access map2, and we're going to encode that into our cache covert channel that's provided by libtea. But because this is ZombieLoad, we're not encoding the actual value at map2, we are encoding data from the line fill buffers. And then we have a handy helper function to create a histogram to plot the data that we're getting. So we can see here that the sibling hyperthread is loading the value x. We've got a little bit of noise, but the signal's very clear. And we can use libtea's paging functions to check that we did actually achieve what we wanted. We cleared the access bit on our second mapping and not on our first mapping. So now we want to take this into the browser. First, we observed that we can get these two mappings we need if we port the PoC to Windows, and then we can rely on memory deduplication. Windows has memory deduplication enabled again within the same privilege context. So we can just set up two arrays with the same values, wait while Windows deduplicates that for us, and now we have two mappings to the same physical page. Windows will also helpfully clear the access bit for us. So that is another privilege building block that we can now do in unprivileged JavaScript. The big question though, can we leak without a flush? What we discovered in our prototyping is that we don't actually need a flush. A speculative access to that first mapping at a different offset at the same time we're trying to access the second mapping still induces a cache line conflict, still gives us zombie loads. And this is a big finding because in the original ZombieLoad paper, it was documented that this CL flush instruction was a requirement. So one of the potential mitigations for restricted environments was instruction filtering to prevent this flushing. But now ZombieLoad is feasible in the sandbox. So here we see SCFirefox. I mentioned the API is very similar by design. So a lot of our building blocks we can port across straight away. As I mentioned, we have that JS API overhead, which means that the transient execution blocks still need to be in pure JavaScript or WebAssembly. So we use a Spectre v1 gadget, a WebAssembly timer thread, and an evict and reload covert channel. But crucially, these have been solved in prior work, so we don't need to reinvent the wheel here, and this doesn't hinder our prototyping process too much. So in our final attack, our scenario is that we trick the victim into opening a link and reading or leaving the tab idle for at least 5 minutes while we wait for Windows to deduplicate the memory for us. We can leak about 1.48 bytes per second with decent accuracy. This is comparable to the Riddle PoC in JavaScript. It is a much lower leakage rate than we see in native code. But we do observe we can have a great leakage rate if we use leverage SCFirefox to do flush and reload. So I think there is potential here to improve the eviction set we're using and actually improve that leakage rate. But that wasn't the goal here. The goal was to illustrate the prototyping process. One limitation is we need to reliably be on the same core. So this isn't yet a full end-to-end attack. So to sum up, I would say this work was a first step towards establishing a methodology and tooling for microarchitectural attack development. There is plenty of work left to do, so much more tooling we could build, and I would like to see the API at an even higher abstraction level so that it's easier to use this for teaching and communicating these attacks to a broader audience. If there's one thing you take away from this presentation, I'd like it to be that we can facilitate attack development and communication by tackling the complexity of our proof of concept implementations. So always keep that in your mind, like how can we hide some of the implementation details and complexity here? And our frameworks are available on GitHub. Contributions, feedback, very welcome. I hope they can be useful to you in your work. And I'm open for any questions.